this work, the microphone? I think that was a yes. Right. So yeah, I'm Pablo. I know most of you already. I'll introduce myself anyway. I'm a postdoc in Montreal and also affiliated here in Flatiron. And I'm going to talk a bit about inference, various inference things. I'm someone who enjoys methods, so it's mostly methods. I'll talk a bit at the end about applying it to large-scale structure, because apparently you need to apply it to something in the end, but I really enjoy just the methods. So normally I start this talk by talking about the difference between likelihood-based and simulation-based inference, but I mean, like everybody knows, sure, I kind of pointed it out already, so I won't do that. And I'll just go straight into my ideas on how we can do better likelihood-based inference. So the idea is, if you have a Planck kind of problem with six parameters, just MCMC, that's solved. But we've heard a lot in this conference about field level inference, and sampling that is not solved. So the idea is we want sampling methods that scale to high dimensions and do multimodality all enough. So I really like nested sampling. I didn't invent this. This is not quite old. But the idea of nested sampling, again, probably everyone knows about it, but is that you start with a bunch of points from your prior, and you slowly kind of converge towards the posterior by sampling uniformly from a region of equal likelihood. So you sample under this constraint here. And as you do that, you kind of zoom in. So like it's much better at multimodality than MCMC because you're kind of zooming into the modes as you progress. So one of the main advantages is that it's very good at multimodality. So one of the things I wanted to talk about a bit is I'm going to talk about a bunch of things. So I'm going to glance through them pretty quickly, but I would love for people to follow up on Slack or coffee or something. But one of the things I want to talk about is this paper, which we submitted recently. Is going to be in the archive. I've been saying that for like in multiple talks now. There's going to be archived soon, but I actually have the archive submission ready now, so it will actually be in the archive. And the idea is that we're actually so the nested sampling. The difficult thing is to sample from these uniform regions, and the idea here is that if you have a differentiable, oh, I'm stuck. There we go. If you have a differentiable likelihood, you can use the gradient of your likelihood to inform that update. And that gives you better performance, particularly better scaling. So this is comparing with other algorithms. Here you see the number of dimensions of your problem. This is a very simple problem, but you see the number of dimensions and number of likelihood evaluations you need. And this is for a fixed number of life points, which is an important hyperparameter in nested sampling. So for low dimensional problems, we actually do worse than things like dynasty. But as you scale to high dimensions, you see that our scaling is much better. So we can take it to high dimensions. And keeping the number of life points fixed, we actually get unbiased inference on high dimensions as well. So we get better scaling with dimensionality. The year here is wrong. And we even could apply it to some small images. So here is a problem where we know the mean and standard deviation. And that's the true one. And that's the one we get with nested sampling. So we seem to do really well. The other idea that I have, I'll come back to nested sampling, but the other idea and the reason I'll come back is that I want to put this together. It's a method that has been developed by colleagues in Montreal and Mila, which is called generative flow networks. So people call this G-flow nets. People develop this for with the idea of drug discovery and stuff like that. So they thought about discrete problems. So imagine you have a discrete problem where these x's you want to sample with some probability that you know the probability. The idea of G-flow nets is that you're going to learn some kind of flow, which you're going to match basically flow in to flow out in every state. So you could imagine that if you're designing words, you could be adding letters. Each state could be adding an extra letter. You're going to basically, if you enforce this flow in equal flow out situation, which is actually called flow matching, you can prove that you get samples with the correct probability distribution as long as the flow at the end is proportional to the reward that you want. So people develop this for discrete problems. We don't have discrete problems in astronomy. I don't know any discrete problems in astronomy. There's probably some, but I wanted continuous ones. So we worked on extending it to continuous problems. So in that case, instead of discrete spaces, you have this kind of hypersurfaces. You can kind of impose the same flow in, flow out condition, and you sample the final state with the right probability distribution. So again, it's just a sampler like an MCMC, but it's a deep learning thing. So basically, once you've trained it, you can generate as many samples as you want from The distribution, so that was in ICML last year, this year, long year. And we've showed that it does toy distributions and it outperforms other methods of limited time. So I will not talk about that too much. If you want to learn more about GFlow-nets, we actually recently had a workshop on GFlow-nets. It's all on YouTube. So it was a 3-day thing. It has basic talks, it has tutorials, it has code. So it's a good resource if anyone want to hear about this. It's a pretty promising direction generally in ML, I think, and potentially for us, for Astro as well. And one direction I'm pretty excited about is the idea of combining GFlow-nets with nested sampling. So we did that in this nested sampling paper I talked about earlier. So the idea here is that you can train a GFlow-net on existing samples, kind of like a diffusion model. And so you could do nested sampling and then train a GFlow-net on top of that. And nested sampling, the promise, it will give you a number of samples per run. But with this, you can then augment your number of samples. So you can get as many samples as you want from a single nested sampling run. And what we showed is that you actually get better samples when you do that than when you just train the GFlow-net, because you have nested sampling kind of guiding where the modes are. So that's a pretty fun direction. We're hoping to test it on high dimensional enough things that maybe eventually we can try and field level kind of problems. That's my likelihood-based part. Okay for time. I'm going to talk about SBI now. Again, normally this part of the talk, I talk about, what is SBI? Why is it interesting? But Chirag already did that again. In fact, he actually showed some of my plots even. So didn't know he was going to do that. But yeah, SBI, we all love it. So instead of talking about what it is, I'm going to talk about an important thing, which is how do we validate that we've done SBI correctly? And this is another paper we had on ICML. And I think people are using it. I know because Sebastian already pointed out a small mistake in the paper, so people are actually reading, which is good. But I think if you are doing SBI, it's a very good way of checking that your SBI is doing the right thing. And it's pretty cheap computationally to use. So the method is based on coverage probabilities, which is how people tend to validate these kind of things. So coverage probability, the idea is that if I have a bunch of simulations and I've learned the distribution in blue and I know the truth in black, basically I want the truth to be in the 95% region, 95% of the time, and so on. So for every percent, I want the truth to be there that many times, right? So if you're in the diagonal, you're good. If you're out the diagonal, you're over or under confident, depending on which side you're in. The idea with our method is that, so normally to do this, you would need to evaluate the probability of the truth being at a given point. And that can be expensive. And if you're doing something like a diffusion model, you just don't get P of X, right? A diffusion model doesn't teach you P of X, it just gives you samples. So our idea was inspired by, if you want to do this in diffusion models, what do you do? And we realized that basically you can use the distances between the truth and the samples to calculate the coverage probability. So it's a, if I'm honest, it's an overly simple trick, but it's something that we realize, and sometimes you stumble upon some low-hanging fruit. And it works super well. You only need samples. You don't need to evaluate P of X, and it scales really well with dimensions as well. We've implemented it. If I'm being completely honest, you can do this, look at this if you go in the source code. It's like 50 lines of code, so you could just code it up yourself really easily. But to save you the time, we've actually implemented it. So if you want to use it, please get in touch or check the repo. And yeah, that's the end of my methods, sadly. So now I talk about actual science, I guess. So SBI, we're trying to, so we actually did SBI on data, not on simulations. We actually applied it to data. Do I have a slide with everyone's faces on it? No, I used to. Well, I'll just name people then. This is work with, 3 minutes, okay. With Chang, who's in the audience, Bruno, who's in the audience, Michael Eichenberg, Chirag, a bunch of other people. I used to have a slide with all their faces, but anyway, we want to do SBI from the SDSS data. So what we do is we take the Quixote simulations, which Paco kindly run for the community. We run a Halo finder. We're using the Rockstar Halo finder. We run an HOD, so we populate these halos with galaxies. And then we add some survey realism so that our data looks like the SDSS data. There's a bit of a lag between my, oh, there we go. This is a movie that Bruno made showing this is the real data, and that's one of our simulations. So you can see, especially when you look at the projection, that you even have the masking effects. So you have some patches that you can see that we actually have as well. So we have pretty, at least realistic looking simulations. And again, validation, methods, person, validation, it's something I personally think is very important. I think, especially as a community, we move towards SBI, validating our analysis is crucial. SBI can go really wrong and you will not know what's happening. So another way, it can go wrong in that the machine learning learned the wrong thing, and that's why my previous paper was for. It could also go wrong in that your simulations were wrong or your forward models were wrong. My previous paper will not pick up on that, so that we call model misspecification. So in SimBIG, we tested on other forward models and checked that we passed coverage test there as well. So we checked that we generalize a little bit. This is very important, and it really affects the constraining power that you have. Skip through this. So these are we have a bunch of papers. I'll just go quickly to the results because I'm running out of time. So this is what happens when you take SimBIG and first compress the power spectrum and you do SBI. That's blue compared to orange, which is a traditional likelihood-based analysis. So we do a bit better. We then did the bispectrum. So that's comparing to power spectrum and to likelihood-based. And we improved it a little bit more on that. We did a wavelet analysis. And again, it does better than the power spectrum and better than likelihood-based. And finally, we did a CNN, so just taking the field, putting it into voxels and running convolutional neural network as the compression, and got some interesting results. This one was particularly interesting in the validation, because if you don't validate, you can get like a teeny tiny thing that passes coverage tests on your forward models, but it does horribly in other simulations because CNN really overfits, right? So validation is really important. All the details are in the multiple papers. Quick mention before I finish to the Learning the Universe collaboration, which is trying to do the same as SimBIG, but on a bigger scale, kind of like Chirac said, for current and future surveys. So doing things much more carefully and in much more detail. And it's funded by Simon's Foundation, so thanks for that. That's my contact if you want to get in touch. And I think I'm right on time, so thanks.
Great. Questions in New York?
Yeah, thank you for the really nice talk. And I really like this like sort of direction of work about thinking how we validate our SBI. I guess one question I have, especially as we think about pushing SBI to like n-body simulations and these things where, you know, it's very expensive to generate new samples of the truth. How do you think about the trade-off between, you know, the simulations we want to use to train a good model that samples well, that has a good understanding of the posterior likelihood, versus the simulations that we need to keep to be able to calculate things like this TARP calibration on a very high dimensional like data set?
Yeah, it's a good point. I mean, I feel like the ML community always does some kind of 80-20 split or something, but I think, obviously, I think the more you can afford to validate, the better. We were actually talking just before in coffee about how to check when you have enough simulations. So I guess if you had enough budget, you could eventually check when you have enough to train and keep the rest validating. But I actually think that the very important test is the one where if you can afford to do slightly different simulations, like a different simulation code or forward model to validate, that's where validation gets really difficult, because then you're checking that. And obviously the real universe is not like our simulation. So that's where you want to, but yeah, I mean, I don't have an exact answer. I feel like it's kind of up to the user and the referee.
Let's move over to Paris. Are there questions in Paris?
Yes, question.
Hi. So yeah, very impressive. One question. So the selection function for spectroscopy can be quite complicated, and I was wondering if that plays into the SBI, which is also very sensitive to a lot of things. So I don't have a lot of experience with spectroscopy, so that's why I'm asking out of curiosity.
Yeah, I mean, we were mostly conservative with our choices. It's true that we didn't really do a specific test about the spectroscopy, whether like changing the selection function a bit and seeing what happens. That could be a good test to do in the future. But in SimBIG, we're mostly quite conservative with things like scale cuts and stuff. We just wanted to get real data constraints for now, but to push to like future things, the spectroscopy could be a difficult thing. I cannot claim to know enough about it to know how to do it properly. But Chang is next, and he knows a lot about that. So.
Okay, if there are questions at Slack, I think you'll take them. So any more questions, please go to Slack. And next up is Chang. Let's thank Pablo again.